Good day, sir. My name is Jaren Thor, and today I will be presenting um, my thermofluid engineering 2 individual assignment, psychometric analysis of a 100% fresh air and mixed air HVAC system. This study evaluate the performance of an air handling unit of or AHU using psychometric analysis. This presentation will be compare the performance of 100% fresh air system with a mixed air system and discuss their energy efficiency. HVAC systems are widely used to maintain indoor comfort by controlling temperature, humidity, and ventilation. In tropical countries such as Malaysia, the outdoor air is hot and humid throughout the year, resulting in high cooling demand and significant energy consumption. Psychometric analysis is an important engineering tool because it allows engineers to determine the thermodynamic property of moist air such as humidity ratio, specific enthalpy, and specific volume. These properties are essential for analyzing cooling, dehumidification, and reheating processes, as well as calculating the cooling load of HVAC system. In this study, I compare a 100% fresh air system with a mixed air system to evaluate their cooling performance and energy efficiency. The objective of this study are to determine the psychometric property of the outdoor activity. Second, to analyze the cooling, dehumidification, and reheating process represented by state 1, state 2, and state 3. Third, to calculate the dry air mass flow rate, moisture removal rate, cooling load, and reheating load. Finally, to compare the performance of the 100% fresh air system with the mixed air system and evaluate the energy saving and achieve through air circulation. This diagram shows the airflow through the 100% fresh air system. The outdoor air first enter the air handling unit as state 1. It then passes through the cooling coil where cooling and dehumidification occur to produce state 2. Finally, the air is reheated to state 3 before being supplied to the conditioner space. In the following slide, each of these 3 states were analyzed using psychometric chart and thermodynamic property. State 1 represents the outdoor air entering the air handling unit. The selected outdoor condition is 35 degrees Celsius with 80% relative humidity, representing a typical hot and humid tropical climate. Based on the psychometric chart, the outdoor has a humidity ratio of approximately 29.04 gram per kilogram of dry air and a specific enthalpy of 109.67 kilojoule per kilogram of dry air. This value indicates that the outdoor air contains a large amount of heat and moisture. Therefore, both cooling and dehumidification are required before the air can be supplied indoor. At state 2, the outdoor air passes through the cooling coil and is cooled to 12 degrees Celsius at 100% relative humidity. As the air temp decrease below its dew point temperature, water vapor condense on the cooling coil surface. During this process, both sensible heat and latent heat are removed. As a result, the air temperature, humidity ratio, and specific enthalpy all decrease significantly. This stage is the most energy intensive part of the HVAC system because it is responsible for cooling the air and remove excess moisture. After leaving the cooling coil, the air is too cold to be supplied directly to the occupied space. Therefore, the air is reheated from 12 degrees Celsius to 16 degrees Celsius. During the reheating, only sensible heat is added. No moisture is added or removed, so the humidity ratio remains constant. The purpose of reheating is to improve occupant comfort while maintaining the low humidity achieved during the dehumidification process. Using the psychometric property obtained from the three air states, the system performance was evaluated. The dry air mass flow rate was calculated as 131.29 kg per minute. The cooling coil removed approximately 2.66 kg of moisture per minute during the dehumidification process. The cooling load required by the cooling coil was 165.19 kW, indicating that most of the energy is consumed during cooling and dehumidification. Finally, the reheating load was only 8.95 kW because reheating only increased the air temperature without changing its moisture content. To improve energy efficiency, the second part of this study investigated a mixed air system. Instead of using only outdoor air, the system mixed 30% outdoor air with 70% return air. The return air is assumed to be at the indoor comfort condition of 24 degrees Celsius and 50% relative humidity. Since the mixing process is assumed to be adiabatic, the humidity ratio of the mixed air is determined using the conservation of mass, while the specific enthalpy is determined using the conservation of energy. Because the return air has already been cooled and dehumidified, the mixed air enters the cooling coil with a lower temperature and lower enthalpy than the outdoor air. The slide compares the performance of the two HVAC systems. The cooling load of the 100% fresh air system is 165.19 kW, whereas the mixed air system requires only 70.58 kW. This represents a reduction of 94.61 kW, corresponding to an energy saving of approximately 57.3%. The main reason for this improvement is that the return air has already been conditioned, so the cooling coil removes less heat to achieve the required supply air condition. The mixed air system offers several engineering advantages. By recirculating conditioned return air, the cooling load and energy consumption are significantly reduced, resulting in lower operating costs and improved HVAC efficiency. However, there is an important engineering trade-off. Increasing the return air ratio also reduces the amount of fresh outdoor air entering the building. If the outdoor air supply becomes too low, carbon dioxide and other indoor contaminants may accumulate, reducing indoor air quality. Therefore, engineering must balance energy efficiency with adequate ventilation to ensure a healthy and comfortable indoor environment. In conclusion, psychometric analysis was successfully used to evaluate the performance of both the 100% fresh air system and the mixed air system. The cooling and dehumidification process accounted for the highest energy demand because both sensible and latent heat had to be removed from the outdoor air. By introducing 70% return air, the mixed air system reduced the cooling load by approximately 57.3%, demonstrating significant energy saving. Overall, this study showed that psychometric analysis is an effective engineering tool for evaluating HVAC performance and supporting the design of more energy efficient air conditioning system while maintaining indoor thermal comfort and acceptable indoor air quality. Thank you, sir.